So there, it appears there's probably several ways you could have done that bonus. Maybe if I have time at the end of class, I'll cover it. I doubt I'm going to have time. We're not having a quiz today because we don't have time. So, all right, y'all ready? Back into it. All right, so last class we kind of finished up. The last 5 minutes I talked about the alternating series test, which is a test that we use on alternating series. And it says if you have an alternating series, remember I told you that this doesn't matter if that's an n or an n plus 1. Doesn't matter if you're starting out as a negative term or positive, just as long as it alternates. And that you can separate the part that's alternating from a sequence, which we'll call a sub n. Then to check for convergence, we only need to do two things. We need to make sure that the sequence is decreasing, and we need to make sure that the limit of the sequence goes to 0. Right? If we can do that, then we can conclude that it converges. If one of these isn't true, the test fails. Right? So the test is no good. All right, so here's an example. Remember, C or D means I'm asking just to see if this converges or diverges. What should pop out at you here is the fact that it's alternating, right? The -1 to the n. So you should be thinking alternating series test. If I do the alternating series test on this, what is the a sub n? What is the sequence I'm looking at? N over n factorial, right? N over n factorial. That's the thing I'm looking at, right? And what I need to check is to see if these two things are true. And I also said here that this means it's decreasing, right? So as you go through the sequence, each of the terms is getting smaller and smaller. However, it doesn't always, in the beginning, it doesn't have to, this inequality doesn't have to hold. It's just that at some point, and then from that point on, it's got to hold. So this says eventually. Okay, this is eventually this inequality holds for some value of n in past. All right, so let's check the two conditions. First, is it decreasing? So we're asking this question. Is this greater than or equal to this eventually? Now, last class I said there were two ways of showing this. One is just algebraically trying to figure out if the inequality is true. The other way is to look at the sequence as a function and then take its derivative and see if it's negative. Could we do that second way on this one? Could we treat it as a function and then do derivative? No, because we don't have, the idea of factorial is not defined on the number line, on all real numbers, so we are stuck with having to show this is true, all right? So I want to see if this is true. So what is a sub n? We write that on the left side. That's just n over n factorial. The question is that bigger than or equal to this, which is plugging n plus 1 into that sequence? Okay, so this is a question. Is it true, right? Is this true or not? So, well, what do you think? Is that true?
Well, the denominator is definitely smaller on the right.
On the right? Left one. This one's smaller. Let's just do some algebra here. Okay, let's just do some algebra. So how about, I'm not gonna cross multiply. I'm gonna multiply n plus 1 factorial here, and that'll kill it. And then I'm gonna do n plus 1 factorial here. Right, that'll be on top. And why do you think I left this n factorial over here and didn't cross multiply? Yeah, because this n plus 1 factorial over n factorial will simplify. I can rewrite that n plus 1 factorial as n plus 1, peeling off the n plus 1, then what's the next piece? And then it keeps going down, so factorial. So we've been through that before. n plus 1 factorial is this, right? So that's no longer there. And do you see those n factorials cancel now? Okay, so let's see where we are now. We are at n plus 1 times, what's still over here? N plus 1 and n. Is that bigger than or equal to n plus 1? Is that true? Yeah. We could divide both sides by n plus 1 right now, couldn't we? Yeah, so if I divide both sides by n plus 1, cancel, cancel, so we get n is bigger than or equal to 1. Is that true? It's always true, right? Because we're going to start at n equals 1. So, okay, the first condition holds. Any questions on the first condition? Sure. I'm getting that look on a lot of your faces like it's almost Thanksgiving. Okay, next step. What's the next thing I have to do? I have to show that the limit as n goes to infinity of n over n factorial is 0, right? So let's figure out what this limit is. So if you try right now and let n go to infinity, you get infinity over infinity. You cannot use L'Hopital, right? Because you can't take derivatives of factorials, but you don't need to, because the factorial on the bottom can be rewritten as what it is, which is n times n minus 1 times n minus 2, all the way down, right, to 1? I mean, that's what it is. And then this n cancel, and you have a 1 up here now. And now you have 1 over n times n times n. When you let n go to infinity, it's going to go to 0, right? So this goes 0. So what can we conclude? It's convergent. Sorry, this one right here, converges. We don't know what it converges to, but it converges. So what if this limit had turned out, like let's say we took this limit and the limit turned out to be 1. What? What then? Would we conclude it diverges? No, we would just say the test fails and we would have to move on to another test. Okay, any questions on that? Yes?
You can just rewrite it as 1 over n minus 1 factorial, right?
Yes. Yeah, you could. You could, yes. All right. So that's alternating series test. It's a great test because it's pretty easy to implement it, right? Just check for the decreasing, take your limit, hope for 0. We're in business. I didn't mention this, but I think I have before. When we're over here and we're like dividing both sides by n plus 1, I thought on inequalities we had to be concerned. Sometimes the inequality flips, right? When you multiply or divide by something. But it has to be negative, right? That's what makes it flip. And we know that n plus 1 is not negative because n is positive. So I'm not considering the flipping only because I know that those are positives that I'm multiplying and dividing by. All right, the next topic here is not a new test, okay? Right now, we're just going to get some definitions out of the way. So the first definition is called absolute convergence. Okay, so this is a definition. All right, a series is said to be absolutely convergent if the sum of the absolute value of the sequence inside converges. A series is said to be absolutely convergent if the absolute value of the sequence inside converges. So let's take a look at an example here. Let's take a look at this one. All right. So that series right there, does it converge or diverge? So does this converge or diverge? How would you go about this one?
Making an absolute value could be 1 to the n over 1 over n. So I think it would still end up being 1 over n, so isn't that divergent?
That is divergent. So if you take the absolute value of that sequence inside, right, it's going to wind up being 1 over n, which is harmonic, which is divergent, right? But I'm asking, does this series converge? So don't take the absolute value. Just how would you go about doing this if you were asked convergence or divergence?
Equivalent thing.
Alternating series test, right? This is an alternating series. So we start with the alternating series test, right? Okay. So if we do the alternating series test here, right? Then first we need to identify the positive part of our sequence, which is the a sub n, which for us would be what? Be careful here. Just 1 over n. Okay, so we'd have to realize that that in there is really negative 1 to the n times 1 over n, right? And so this is the part that's not attached to the alternating, right? So there's our sequence that we're looking at. Now we need to check the two conditions. First condition, is it decreasing, right? Eventually, is that true? So let's just check that. What's a sub n? 1 over n. Is that bigger than or equal to 1 over n plus 1? Cross multiply, this checks. It's a pretty easy check on that. Okay, part 2. Does the limit as n go to infinity, as n goes to infinity of 1 over n, is it 0? Yes, right? So check. So what does this series do? It converges, right? This converges. Got it? That is a convergent series. Is it absolutely convergent? No. It is not absolutely convergent. To be absolutely convergent, you would need the series, the absolute value of what's inside of it to converge. So if we go and we look at this, yeah, I can erase this. If I take a look at, take that series and take the absolute value of it, then that is equal to that, which is harmonic, which diverges. So it is not absolutely convergent. Okay? What is not, so I'm saying what is not absolutely convergent? I'm saying something's not. What's not? That series, right? That series is not absolutely convergent. It's convergent. It is convergent by itself. It's convergent series, but is not absolutely convergent. What was your question, Michelle?
Are any alternating series convergent? Or absolutely convergent?
Sure. We should be able to come up with one. Yes. You would just need, the series and its absolute value to converge, right? So I'll give you an example. Just change that to n squared. Okay? If I change that to n squared, right, then this becomes this, that becomes that, this becomes this, that's squared. You can still check that this inequality will hold. You can do the algebra on that. It will hold. 1 over n squared goes to 0, so it converges, right? So we would have convergence here. But then when we come over here, right, we do this, we get to that. And what is that? Why?
Because it's approaching 1 much faster. Approaching, yeah, 1 much faster than 1 over n is.
That's not, that argument's not going to work.
Okay.
It's a certain type of series.
Oh. P series.
That's a P series with P being 2. There, that's all you have to say. And we're done. Okay? I mean, with what you were saying, that's like, I'm not quite sure what you mean by it's going to something faster. So this right here, right, wouldn't be harmonic anymore. It'd be P series. And that converges. So it would be absolutely convergent. Okay?
What would that look
this series, that series, would be, are you saying as a series or as a sequence? Because remember, the series is adding the things up. Look, let's look at this as a sequence first, just that, right? It's going to start, you're going to basically be like scattering like this, but approaching zero very fast. Positive, negative, right? And then adding those up. We have concluded that if you add these up, like add that number, and then you basically add that number, which means subtract, and then add, and then subtract, add, subtract. If you do that, it's going to converge. That sum is going to converge to a number. I don't know what it is, but it's going to converge, all right? If I go and I take the absolute value of that, then all that does is it moves all these dots that were on the bottom up to the top, right? Absolute value, and these are no longer here. If we add up all these, it still converges. But when you made that n, then it looked a little different. It was still this scattered, but they weren't getting close to zero that fast. The alternating series does converge, because you have positive, then you negative, positive. That does converge, but when you take the absolute value, it became harmonic, and those came up, and those added up were not getting small fast enough, and it diverged. Does that make sense? So all of that is dictated by that number, right? If that number is bigger than 1, we're going to get convergence. If it's smaller than or equal to 1, we're going to get divergence. Okay. Well, over here, all right? Over here, that's not necessarily the case. We have to run the alternating series test. Okay, was there another question? Okay, we have another definition. Definition is of what's called conditional convergence. If a series converges, but the absolute value of it diverges, then the original series is said to be conditionally convergent. Those are the only two definitions we'll have, so don't worry, there's not like 5 different types of convergence. We have absolute convergence and we have conditional. So this series right here, the one that we started with, right? The one that was harmonic when we took the absolute value, right? That's a conditionally convergent series. Because this alternating series, right, when those blue ones are gone, that thing converged, didn't it? But when we took the absolute value of it, it became harmonic, and that diverged. So that is an example of a conditionally convergent series. Okay? It wasn't absolutely convergent, but it is conditionally convergent. Now, the last thing we have before we move on to the next test is a theorem. And the theorem states that if the absolute value, so if you have a series, you take its absolute value, if this converges, then of course that must converge. It's impossible for the absolute value of a series to converge and then the series without the absolute value to not converge. That's impossible. I mean, just think about it. Like, this series might have like some things that are positive and negative, positive and negative. It might have things that are alternating, right? So if we take the absolute value of this, then you're making everything that was negative positive, right? And if we add all those up and we converge, then this with stuff taken away should also converge. right? This has got to be like less than that, and so it has to converge. Make sense? Okay. So, but doesn't this mean a series is absolutely convergent? Right? Isn't that what that means? So another way of looking at this theorem is that absolute convergence implies convergence. So if you can show that the absolute value of a series converges, then you basically have concluded the series itself converges. You don't have to do any work. I'm going to show you an example. I'm going to show you an example. Okay, let's look at this one. Sum n equals 1 to infinity of sine n over n cubed. And we haven't seen one of these yet. So what I want you to notice is that this is not an alternating series. I mean, I do agree that as we plug in different values of n, right, or 1 and 2, and do sine on our calculators, yes, we are going to get positive numbers and negative numbers. They are going to be different signs, but it's not going to be like at 1 it's positive, 2 it's negative, 3 it's positive, 4 it's not going to switch. It'll be sporadic. Does that make sense? So this is not an alternating series, so you cannot use the alternating series test. Right? Okay. So what can we do? Why don't we look at the absolute value of this? Okay? Let's look at the absolute value. The absolute value of this series, this is very important that you understand the logic of why I'm doing this. So let me run through this and we'll kind of, at the end, I'll kind of do it again. Let's look at this. So let's say, consider this. Okay. Consider the absolute value. If I can show that that converges, right, then that has to converge, right? Okay, that's what the theorem is saying. Now, why did I take the absolute value of it? Because I want to do a comparison. Okay, I want to do a comparison. And the thing about the comparison test is that what are the conditions on the comparison test? If you look at your table, right below the two sums, right below the two sums says sum, then below that it says a sub n greater than 0, b sub n greater than 0. See that on your sheet? It means, look, if you're going to use the comparison test, the thing in here has to be positive all the time. And so if I don't do this, then I can't use the comparison test. So you can't do that on an exam. You can't just be like, oh, I'm going to compare this to a p-series, 1 over n cubed. You can't use comparison. You have to do this step first. Does that make sense? Okay. So now I'm going to use comparison test. So I'm now going to compare this to a p-series. Now I'm only saying p-series because, David, you said p-series, didn't you? I did. And I'm thinking 1 over n cubed?
Yes, sir.
Okay, so yeah, I think this is a reasonable thing to compare to because that has an n cubed. Sine is bounded between -1 and 1, and we're taking the absolute value of it. So, I mean, this seems reasonable, and we know what this does, right? This p-series, this converges. Okay, so this is p-series. We get convergence here. So now we're going to do one of two things. You're either going to do an inequality or you can do limit comparison. I'm going to do the inequality just because. So which one am I doing? On the sheet here, am I doing I, double I, or triple I? Triple I is the limit. I'm saying I'm not going to do the limit one. So I'm doing I because the one I'm comparing it to converges, right? So I'm doing I. So on I on this sheet, I want to show what? I want to show that the a sub n, which is what? What is the a sub n for us? This is what I want to show. A sub n is the one we're starting with, which is the sine n over n cubed in absolute value. In the absolute value, right? Is less than or equal to 1 over n cubed. And I think this is pretty easy to show because this is the absolute value of sine on top over n cubed on the bottom. Right? Hey, welcome back. How you doing? Good, good. Okay, so absolute value of sine on top, n cubed. I don't need the absolute value because I know n is positive, so n cubed is positive. And then here, and then I can just like cancel out the n cubes, really, like cross multiply and they're both gone. So my next line is this: the absolute value of sine of n less than or equal to 1. Do you agree that that's true? That's true, right? Sine is bounded between negative 1 and 1. So I take the absolute value of it, the biggest it's ever going to be is 1. And that's okay if we're equal. We just have to be less than or equal. So this inequality holds, right? So by the comparison test, I know that this inequality holds, which means whatever this does, right? Whatever this does. And since this is the absolute value of the series, by the theorem, that converges. Got it? Questions?
I got it.
All right. Okay. All right. So now I conclude. Therefore, I need a final statement. Therefore, sum n equals 1 to infinity sine n over n cubed converges. Okay. So that is a good illustration of how you can use that theorem. And is that theorem anywhere on here? It's the very last row. See that? If the absolute value of a series converges, then so does the series itself. Are we good? We're moving on. And we have come to the best test, of my favorite test, the Big Daddy, the head honcho, the one we're going to use a lot more. All these other tests are great, but in my opinion, they pale in comparison to this one because of how useful it is to us in a little while. The almighty ratio test. The almighty. Maybe we should put that up there. The almighty. The almighty. I'm quoting that. That's my thing, okay? That's not in the book. The almighty ratio test. And it's on here, okay? It's on here. So let's look at what the table says. If we're given a series, right? And notice that in that little box, it gives no conditions on this series, does it? Like it doesn't say that these have to be positive. This is not a test that you only use when it's alternating. I mean, this works for every series, all right? Well, I'm sorry. You can apply it to every series. It's not going to work for every series, but you know, if it was, then we wouldn't do all the other ones, right? I mean, this test does fail sometimes, but so we start with anything. What we do is we take a look at something. We consider this limit. And what it is it's the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. What this is doing is it's saying, hey, look, if we have this series, if we were to write the series out, it would be like a sub 1 plus a sub 2 plus a sub 3, and that goes forever, right? What this is saying is, let's just go out and look somewhere out in this thing. Here's a sub n, let's say, and the next one is a sub n plus 1, right? And then it keeps going, right? But let's say I go out and I look at these two terms that are side by side, and I take the ratio of this one divided by that one. right? The ratio of that divided by that, and take the absolute value. This test says that this limit is going to give us some answer, L, right? The ratio of that divided by that should be some answer. And if the L is less than 1, we get convergence. And if L is what, greater than 1, we get divergence. And when it says greater than 1, it even says there or infinity. So if this limit is infinite, you get divergence. If the limit is 2, you get divergence. If the limit is less than 1, you get convergence. So what we're saying is we're taking a look at the ratio of those two numbers and saying, hey, look, if that number, if this divided by this is smaller than 1, then what's happening is these things, the ratio is approaching basically something smaller than 1, so it's going to converge. But if this ratio is bigger than 1, it's kind of like adding up too fast as it moves out. And so it'll diverge. What does this ratio test not cover if the limit is 1? And if the
It was 1, but we knew it's not alternating, would it work?
if the limit was 1, but it was not, well, more than that, if this was a positive series, right? If the limit was 1, are you talking about like the end term test?
If we get a limit of 1, is there something we can check for to see if we can still get like useful information out of it? Because if it's the same ratio, it means that each term is the same, right? So either it's alternating, which wouldn't help us, but if it was all positive, we know it's divergent.
Well, it's approaching 1, right? It's
Yeah.
different than being 1, right? So that you can approach 1, but that ratio, if it were 1, yes, then you could pretty much conclude that there's the same distance between each one, right? Let me think about that a little more. This test is inconclusive if we have 1. I think if we knew what the series we were looking at was, maybe we could use something else, and that 1 would be useful. Normally what's going to happen is if we do get 1, we're going to just do a different test. Or maybe we never even would have got to 1 because we would have used a different test anyway when we looked at the series. For what we're headed for, okay, we are going to get 1 sometimes, and we're going to have a way around it. Like we're going to have something we do. So yes and no, I guess is your answer. Okay, can we run through an example here? This great almighty test. Okay, here's an example. Sum n equals 1 to infinity, negative 1 to the n, times n squared over 4 to the n. All right, so let's just think about a couple of things here. It's an alternating series, right? So you could use an alternating series test here. We could also take the absolute value of it, right? And then if we do the absolute value of it, we might be able to compare it to something and hope for convergence, because if we get convergence, then the absolute value converges, then that converges, right? So there are a lot of things you could maybe try here. But I'm going to try the ratio test, right? So here it comes, ratio test. So I'm going to do the limit as n goes to infinity of this ratio. Okay, now what goes on top? It's the sequence replacing all the n's with n plus 1s. Okay, so we've got negative 1 to the n plus 1 times n plus 1 squared over 4 to the n plus 1. Do y'all agree that's me replacing all the n's with n plus 1s? And then I'm going to divide that by the sequence itself with just n's in there. So just the sequence, right? Just this. So negative 1 to the n times n squared over 4 to the n equals, okay, limit n goes to infinity. Let's consider a couple of things first. What about these? They're gone, right? Does not matter. We get ones or negative ones. Absolute value is going to kill those off. So those are completely non-existent, right? And then everything else is going to be positive, but I'm going to leave the absolute values here. And I suggest you leave them also. Let's see what we're left with. We're left with this fraction over this fraction, right? This over this. So what I'm going to do is I'm going to write this fraction and then the reciprocal of this one multiplied, right? So I'm going to do n plus 1 squared over 4 to the n plus 1 times 4 to the n over n squared. Y'all agree? Now what?
Multiply. Or cancel out, excuse me.
Rewrite this as what? 4 to the n times 4, right? That's what that is. And now you get the cancellation, don't you? So those are gone. That's nice. And so really here, what we have is the limit as n goes to infinity, absolute value. On top, the only thing I have left is n plus 1 squared, right? So I'm just going to expand that, n squared plus 2n plus 1 over the bottom, which is just 4n squared. And that limit you can do. That's, you know, infinity over infinity, L'Hopital, infinity over infinity again, L'Hopital, and you're going to get 1/4. And since you get 1/4, we now check. Is that bigger than 1 or less than 1, right? So this is less than 1. And therefore we have what? Convergence. Converges by the ratio test. Okay? Any questions? This splitting up of the 4, very common in ratio tests. It's kind of the whole reason it works so well. Yes?
So it converges, but it doesn't converge to 1/4, or it does?
It does not converge to 1/4. It just converges. We still are very limited. Remember, there's only 2 series that we know the convergence of, 2 types of series that we can get convergence, and that's geometric as long as the absolute value of r is less than 1, and telescopic if we can find the pattern of cancellation. Other than that, there's a possibility that, depending on if people want it, I usually don't have time to cover it in the Cal 2 class. I have this like hour and a half lecture that I like to do, offer as like totally optional, no bonus points. You show up if you want to show up. I usually do it during finals week. And it's me covering Fourier series, which we don't really get into Fourier series here. So I talk about Fourier series, and the entire hour and a half lecture takes us from a series where we're adding up a bunch of terms, and the whole hour and a half is all the work that it takes to find the sum of that series. So finding the sums of series is not, in general, easy to do, unless it's geometric or telescopic. But most of the time, all we need to know is whether or not it converges or diverges. I know that may not seem like that's reasonable, like you would need to know what it adds up to be. Just hang tight. It's where we're headed with this, okay? All we need is the convergence or divergence to do what we need to do. Yes?
For exam purposes, are you going to specify which one you want, or do you just say it's open season, see if this is convergent or divergent, use whatever method you see?
Oh yeah, the final, I'm just going to give you a series, and you've got to just figure it out.
Very good.
Yeah. So there's no prompting like, hey, use the ratio test to.
I'm with you. I'm
Yeah.
just clarifying.
Yeah, no, yeah, that's part of what makes it hard.
Sure.
Yeah, that's part of what, it's kind of like the integrals. You know, your first test, we had only gone up to, I think, integration by parts, and that was good because then you knew those were the only techniques. On the next test, you had all the techniques, so that made it a little more complicated. By the time we get to the final, if I give you a series and ask for convergence or divergence, we've got all the tests, You know, so that makes it challenging. Yep. Okay, ratio test. Nice, beautiful. We should do another one. Okay, here we go. Can I use the ratio test? You can always use the ratio test, all right? You can always use it. May not work. If we get a ratio of 1, then it fails, but let's at least go for it. Now, I am in no way saying that from here on out you should just always break out the ratio test. You should always be looking and considering, is there an easier way? Okay, because sometimes the ratio test can take you very, very far down a path of limits that you don't want to have to do the algebra for. So, okay, so I'm going to do a ratio, right? And on top's going to go what? Absolute value. Top's going to go that with everything replaced with n plus 1. So be real careful with that. That's n plus 1 raised to the n plus 1 over n plus 1 factorial, right? That's what that is. And then the bottom one is just going to be the original sequence, right? Okay, now that's it written out, correct? From here on out, I'm most likely not going to write this step anymore. Here's where I will start from here on out. Okay, so I will start by doing this. It just saves us a little bit of time. So I will start there. Instead of writing it as a fraction over a fraction, I'm going to write it as this fraction times the reciprocal of the sequence. Okay? It just saves a little bit of time. But you all understand what I did, yes? Okay, so what should I start trying to do here? Reduce out the factorials, right? Because that factorial does simplify. This one becomes, peel off the n plus 1, n factorial, and then those n factorials are gone. Ooh. Okay. So. Okay, so I'll do that. Yeah, no, you got to do something, right? You got to try something. So you're suggesting to rewrite this as n plus 1 to the n times n plus 1. Why? Because we can, right? Let's try it. Okay, that's all that's on top? That's all that's on top, right? Yeah. What's on the bottom? N plus 1. Times n to the n. Well, that's not that bad. That cancels, right? Now what? Limit n goes to infinity, absolute value of n plus 1 to the n, right? Over n to the n, right? So I'm going to rewrite it as that. What is that? Okay, as n goes to infinity, where's that headed? Infinity over infinity. So if you did L'Hopital on that, where would that be going? That would be going to 1, right? Do you all agree that's headed to 1? 1 to the what? 1 to the infinity, which is? Indeterminate form. This is an indeterminate form. Isn't it? This is a limit where we don't have the answer because it looks like 1 to the infinity. Did I tell you that story about that former student of mine that called me like 2 years after Cal 2 class. He was off doing engineering at some other university and he didn't get mad at me, but he was like, you know, why did you tell me? You always said that 1 to the infinity was indeterminate form, and I'm sitting here doing this problem and it's not. And I'm like, what? And so he had to explain to me. He had a problem where basically it was the number 1 raised to a power that was getting bigger. And that's 1. Because it was the number 1 raised to a big power. This is not the number 1, okay? That is, in the limit, this number is approaching 1. It's never going to be 1. Plug any value of any 1 in there. It's never going to be 1, right? Correct? Yeah. It's approaching 1, but it's not 1. And you raise that to a huge power, and it's indeterminate. If I say, what's n over n to the n, now it's 1. Because that is 1, right? There's no limit involved here. That is 1. And 1 to any power is 1. So, indeterminate form. So what do? Just say it diverges? No. We do this. We go back and we treat it how we treat indeterminate forms that look like that. So I kind of need to keep going here, and I'm going to lose the absolute value because it just might make it look a little easier. That just looks a little nicer without the absolute value. Now, what is the technique? Somebody please make me happy here and tell me what the technique is when you have 1 to the infinity. You have to bring in a natural log. So basically you have to say, okay, I'm going to call this thing, let's call this limit, let's call it y or something. And then we take the natural log on both sides, and that allows you to drop the n down and do all this stuff. Now I'm going to save us the time because we don't have it. I'm going to do one more thing before. I'm not going to do that right away. I'm going to do this first. That's what that limit is. So I split that into that fraction 2, right? N over n and 1 over n, like that. Does anybody recognize this limit? That's e. Okay? I suggest you start, like you get to the point where you can recognize that as e. Okay? This is, I think when I may have done it, I know in my Cal 1 class I do this. I do this example for the exact purpose that is e. So if you do all this y equals natural log drop down and do all that, play that game, you will get e here at the end. So I'm not going to go through the steps, but that's e. And what can you tell me then? E is bigger than 1, right? And so what does this series do? Diverges. Who did that? Whose side? Okay. My college algebra class today, we were going over something. We were doing logs and stuff, and one of the students was like,
Oh, college algebra.
and it wasn't like I'm tired. It was like, why am I here?
College algebra wouldn't be nice.
Okay. Moving. If this were, I can't use n because I'm already using n, but if you replace that 1 up there with like k, then the answer is e to the k. This number above the n is always the power on the e, but that, in this case, it was 1, so. Okay, we are proceeding. All right, there's another test, the root test. And I'll say the root test is kind of like the ugly duckling, I guess. Not really, not really used that often, but useful when it comes, when it does show up and you need it, it's nice to have it. It just says this. Again, the root test is if you're given any sequence or any series, okay, then if the nth root of the absolute value of a sub n, I forgot to put limit, sorry. Forgot to put the limit there. If the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to L, then we will get convergence if L is less than 1 and divergence if L is greater than 1. So isn't it the same sort of thing as the ratio test? Like we're going to take a limit, right? And we're going to figure out what it is. And then we're going to ask ourselves if it's less than 1 or greater than 1. But the limit we're doing is not the ratio, is it? It's the nth root of something. So I'm going to show you an example, and you'll see this, how this root test is used. So as your example, I do not believe we have seen a series like that. Now, could we use the ratio test? We could try it, right? But this is set up for the root test. It's perfect for the root test. Because the root test is a test we run. And what we do is we recognize that we're going to do the test, the root test, we're going to take the nth root of this, right? And look at this thing, this whole thing is raised to the nth power, right? So when I take the nth root of that, basically the power and the root are going to cancel each other out. And then I'll be left with what's inside. And I'll be taking the limit of what's inside. And that's just what? The limit of that as n goes to infinity is just 3/5. So 3/5 smaller than 1. This is going to converge, right? But let's run through the test. Okay, so the root test, I'm going to take the limit as n goes to infinity of the nth root of the absolute value of that. Now, I don't need to consider the absolute value because I know the inside's positive, and positive raised to a positive power is just going to be positive. So I'm just going to do 3n plus 1 over 5n plus 3 to the n. I'll continue over here, which is just limit as n goes to infinity of the root and the power cancel, 3n plus 1 over 5n plus 3, which is 3/5, which is less than 1. Therefore, we get convergence by the root test. Isn't that nice? Isn't that a clean test? If you have something, the whole thing raised to the power n, I suggest you try that test. All right. That's it for that section. Yes. That's all the tests. Yes.
So if it was raised to to the n plus 1, you just split it and then add up the...
If it was, yeah, you could do that. Mm-hmm.
You could do two different nth roots.
Are you saying if it was n plus 1, then you could do, one of these, and then the other one would be the nth root of just that thing without the power. I mean, you still have the root, but you wouldn't have the power there.
So if you took the nth root of, or you did the root test with n plus 1 in the power, how would the nth root get rid of them? I mean, because
No, you would rewrite this. So instead of n plus 1, you'd write.
Oh, and it cancels out.
Like that. That would be n plus 1,
oh,
right? And then you can do the root on both of them. So that one would cancel. That goes to 3/5. And on this one, you would still have to figure that out. But,
I see.
yeah. Okay. We're ready. We're ready. We're ready. Give you just a real quick glimpse before we start this section. Just a quick glimpse into what we're trying, like what we're headed towards, okay? So I want everyone to consider the following function. F of x equals, let's go with just cosine x. We should all be very comfortable with what this function looks like, right? Not yet. I'm just trying to motivate the next section, all right? And the next, like, 3 sections. All right, so we all know what cosine of x is, right? So maybe you're working in an engineering or physics problem or whatever, and you've got somewhere in the problem you've got cosine x in there. A lot of times, we won't use cosine x. We'll replace cosine x with a different expression. All right, so we get cosine x appears, and then all of a sudden, let's say instead of using cosine x, use 1 minus x squared instead. Okay, and then you're like, oh, you know what? Hold on, x squared over 2. Okay, they'll say use that instead. And you're like, what the hell? How am I allowed to replace cosine x with 1 minus x squared, right? And are they even close to being the same thing? Well, they are very close to being one another near 0. So if you have a calculator, I would ask you to do this. We all know what cosine of 0 is, right? So we're just talking about what's happening near this point right here. What is cosine of 0? 1, right? Okay. So let's plug 0 into this and see what we get. 1 minus 0 squared over 2. That gives us 1, right? They match up exactly right, right? Does that mean they're the same? No, it's not the same. But let's try something close to 1. Close to 0. So let's try something close. And when I say close, I mean let's be pretty close. So let's try, so this checked out, right? Let's try cosine of 0. Let's get pretty close, 0.01. So on your calculator, make sure you're in radians. What do you get there? 0.999? How many nines? 4 nines and then a 5. Okay, let's stop there. Okay, let's try that in the other one. 1 minus 0.01, that quantity squared over 2. And tell me what you get there. You get 0.99995. It's pretty close, I would say. You did it, right? Okay. So when we're at 0.01, we're pretty close to the same values, yes? Let's try another one. Let's try moving out a little further. How about cosine of 0.1? What is that on your calculator? 4 nines again? 2 nines and then a 5? Okay, now try 1 minus 0.1 squared over 2, and what do you have there? Same? Damn, that's pretty good. Okay, do they match on the next decimal? Did anyone check the next decimal?
No.
No? This one's 0.995? 004? And what about this one? Oh, it just stops? So we're off a little bit, right? This is like, that's zeros forever. So we're off way out here at the